Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Dave Ansell. Now, first of all, Dom has called in, and he does it every week. He always has a question. You must think about it all week. He says, what about mobile phone masks? He wants to know how much radiation do they emit, and does this radiation affect humans? Dave.
OK, a mobile phone mast, we say it's giving out radiation, but it's not the same kind of radiation which a radioactive material will give out. Basically, radiation means something which will travel out in straight lines from a point, so it's going along a radius of a circle or a radius of a sphere. So there are lots of things which are radiation. Light is a form of radiation. There's ionising radiation, which is a really nasty stuff which you get from radioactive materials. And mobile phones basically work on microwaves, so similar to the sort of things which you use in a microwave oven. They give out sort of several tens of watts, so similar to a normal old-fashioned light bulb, that amount of radiation. Now, as far as we know, the only damage that microwaves can do to you is by cooking you, so by making you hot. If your body absorbs some microwaves, it'll warm up, and if you absorb an awful lot of microwaves, then you can start doing damage by actually sort of heating up your flesh and actually doing damage. So a mobile phone mask, it's only producing giving out as much energy as a normal 100-watt light bulb at the most, and that's quite a long way away from you, and you can stand really close to a 100-watt light bulb without it doing you any harm. Your actual mobile phone is going to give you far more energy density near your head than a mobile phone mast, unless you're actually standing right next to it. And mobile phones don't seem to do anybody very much harm. As far as we know, there have been some studies which have shown that it actually seems to make people slightly more intelligent if you run a mobile phone next to their brain, which is slightly interesting, but certainly nothing serious, as far as we know, nothing cancer-causing or anything like that.
Interesting stuff. Thank you, Dr. Dave. Our next question is about batteries. Dave in Great Yarmouth says, I often see a wide variety of batteries when I go to buy them. How do they make the batteries last much longer than they do the cheaper brands?
Basically, a battery is a chemical reaction which can push electrons around a circuit. Depending on which chemical reaction you use, it'll push electrons different amounts. So that's called the voltage, so how hard you're pushing electrons around the circuit. So some batteries are higher voltages than others. The lithium batteries will have 3 volts, whereas it'll push each electron out with 3 volts of force, essentially, of voltage. And things like zinc-carbon batteries and alkaline batteries are about 1.5 volts. And there's lots of other voltages in between with different chemical reactions going on. And basically, in this chemical reaction, each atom inside the battery can transfer either 1 or 2 or possibly 3 electrons, and then those can go around the circuit. So how long your battery lasts is to do with how many electrons it can push around the circuit before the chemical reaction dies. So it depends on sort of how much reactant you can get inside the battery. Different chemistries, you can shove more stuff in than others. So an alkaline battery, you need less electrodes, and the materials you're using are denser, so you can get more active chemicals in there, so it lasts longer. And lithium batteries, you need half as many of them because they're twice the voltage. Also, you can get a very high density of chemicals in there, so they last a very long time.
One thing I want to ask you is that I had a zappy thing, like a charger, which went west, because I lost the actual the charging wire to charge it with, and then it went a little bit low, but it wasn't completely empty. But then all attempts to try and recharge it, just not happening. Do they?
What kind of battery was it?
It was, one of these things that you zap your engine with if your battery's gone flat, and it just helps your engine start.
Some types of battery, that's probably a lead-acid battery, which is the same kind of battery as is in your car. And those really don't like being discharged. You get other chemical reactions going on which break up the structure of the battery. And if they're left discharged for a long time, then it ruins them, and it won't hold charge anymore. So it depends on the kind of battery. Lead-acid batteries you want to keep charged all the time. I think lithium ones similarly. Rechargeable lithium ones that you get in mobile phones and computers. Whereas others, like the rechargeable NiCads, don't mind being discharged, but they don't like really being charged and discharged too many times.
So we'll fire up the camper. Let's go to the phones right now. And we've got Tony on the line. Hello, Tony.
Hello, light of my life.
How are you?
Very well indeed.
Jolly good. What's your question?
Well, I watched a very interesting program on the box about high-speed photography. And one of the things they showed was lightning, and they proved that it went backwards, if you know what I mean. Instead of starting in the cloud, it started on the ground and went upwards.
Yeah.
Now, I can understand it in the clouds, you know, but where does it get its power from the Earth? They did mention something called a sprite, I think.
With sprites, strange effects at the tops of clouds. The energy is actually coming from the cloud. So what happens is there's various things inside a cloud which I don't think is very well understood, which causes bits of the cloud to get a very, very large charge. It gets very, very charged in the cloud. And then this means that... So I've pretend it's positively charged, don't quote me on that. So if it's very, very positively charged in the cloud, then that will attract electrons from the ground. And then so they will then start flowing up to the cloud. And so because the ground is will conduct electricity reasonably well by the sounds of lightning, and these electrons will flow up from the ground up to the cloud, but the energy is coming from the cloud. It doesn't really matter which way
it's not coming
the currents
from
flow.
The ground, no, I understand. Bye.
Take care, bye-bye. Our next question, Dr. Dave, comes from Jackie, who's asking about soil, saying, hi to both of you. Given that the soil is depleted of many minerals, how much longer can the land be sustained at the current rate of use? And the layer of soil is surprisingly thin in many places.
I mean, it'll depend exactly where you are, how quickly you're depleting the minerals. Soil is being made all the time. Particularly plants and weathering works their way into rocks. They cause the rock to break down, and the rock gets smaller and smaller lumps until you essentially get soil. And this releases nutrients and minerals. There are people worried that basically if you're farming really intensively, then you're sort of sucking those minerals out all the time. There are strategies involving basically putting crushed rock onto soils in order to regenerate them, or you can essentially add the minerals back onto the soil. I certainly can't give you a number. I think a bigger problem is actually the soil itself washing away or blowing away. In lots of places, certainly East Anglia, the level of the soil is dropping quite fast because it's peat. And when peat dries out, if it gets very, very dry in a very hot summer, then it sort of essentially it's just organic matter. It oxidizes with the oxygen in the air and essentially just disintegrates, and it will blow away. And there's lots of other places where the soils, because people aren't farming them in a sustainable way in order to hold the soil on the surface, things like which direction you plough around a hill. Like in some places, if you plough up and down the hill, then you get lots of lovely runnels for the water to run down the hill. If you go around the sides, then it sort of traps the water and stops it washing all the soil away. And there's all sorts of tricks like that. But yes, it is certainly a worry, but we'll have to see what happens.
Alan in Orpington is on the phones. Hello, Alan.
Yes, hello there.
Hello there, you're through to Dr. Dave.
Hello, Dr. Dave.
Hello.
Yes, this is a question that I don't think you're going to have an answer to. We're told by the Water Board in London that as the water goes down the Thames, it passes through the kidneys of the population at least 3 times. Now, what interests me is what relevance has that to the sea? Is there an amount in the sea that has passed through the human population over many years through the kidneys? And has it also, if we go back to dinosaur times, been passing through kidneys of animals and human beings going way back?
It certainly has. You drink water, it passes through your body and then it passes out again. I guess you possibly urinate a couple of litres a day. And so if you've got 1 billion people, then that's going to be a couple of million tonnes of water every day going through people's kidneys. And if you multiply that back through millions of years, then I would have thought most of the water in the ocean will have gone through some kind of animal's kidneys. Quite a lot of it won't have gone through human kidneys, because apart from anything else, some of the water in the really deep sea stays down there for thousands of years. So when it last was near the surface, there probably weren't very many humans about. But certainly through animal kidneys, and a lot of the water you drink will have gone through dinosaur kidneys.
So just taking it one step further, there's got to be certain areas, I would have thought, on the planet where the water, like in the ice caps and places like that, that could never have passed through any animal's kidneys. It will very likely been there from whenever to the present day and never passed through an animal's kidneys.
I think the only water that you could say that for was water coming out of either comets hitting the upper atmosphere, which are made up of water, or water coming out deep from deep under the earth, and even the water deep under coming up in volcanoes and things. That could quite a lot of that has sunk down from the surface. The ice caps certainly haven't been there throughout the Earth's history. I think the Antarctic ice caps are only a few million years old.
So there'll be dinosaur material.
There'll certainly be. We've gone through dinosaur kidneys and lots of mammals. I mean, dinosaurs were 65 million years ago and further back. So they've gone through lots of mammals. Could have gone through lots of mammals since then, and lots of insects and lots of everything else.
All right, Alan.
Right, thank you.
Thank you very much. Take care. Bye-bye.
Bye.
Bye-bye. Now, Dr. Dave, if the Northern Lights were 100,000 miles out in space, would the naked eyes be able to see them? And what would happen if an astronaut in space walked through them? That's from Mike.
Okay, I'm not sure. I mean, the Northern Lights tend to happen at about 100 kilometres, 150 kilometres up. They're created by the solar wind. These are energetic particles, so things like nucleuses of hydrogen atoms, protons and electrons being thrown off the sun in something called the solar wind. Sometimes you get really, really violent explosions on the sun which sends off huge amounts of this solar wind. When they crash into the Earth's magnetic field, they get trapped along the field lines of the Earth's magnetic field, and they pile into either the Earth's North Pole or the South Pole. They've got lots and lots of energy. They're moving at thousands of, definitely kilometres a second. I think probably tens of kilometres a second, if not hundreds. I don't have the number in my head. And they pile in there, they give that energy to atoms in the atmosphere, sometimes nitrogen atoms, sometimes oxygen atoms, and then those atoms glow. And these particles interact with the magnetic field in complicated ways, so you get these curtains of light moving around. And now, because you've got these high-energy particles, they're actually a form of ionising radiation, the nasty stuff. They can bash into your body and knock chemicals apart, and then that can cause all sorts of havoc. You can damage your DNA, which can lead to cancer. And if you get it really serious things, you can actually just stop the chemistry working and you get radiation sickness. So it certainly wouldn't be good for a astronaut to be standing in this stuff, because it's basically he's getting a really high radiation dose. And if he stayed there long enough, he would certainly get cancer and could possibly get radiation sickness. If they were 100,000 miles out into space, I don't think they're very dim. I personally have never seen them. I would have thought if they get out that far, you'd have difficulty seeing them. Although the particles are there, there's nothing for them to hit into, and so there's no light being created anyway. So they're not that high. But even if they were, I don't think you'd be able to see them.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Let's now go to a question from Mucker in Kingsthorpe. He says, once the TV set is on, does that give off any radiation?
Depends what kind of radiation you mean, and depends on your type of TV. Modern liquid crystal, modern flat screen computer monitor, they pretty much only give out light, which is, of course, a form of radiation, so strictly, yes, it will give out radiation. That's the whole point of a TV monitor. The old cathode ray tube TVs, I think they can, basically you've got, the way they work is you fire electrons from the back of the TV set in something called an electron gun. You then steer that with some coils, and they hit the front of the screen, and where it hits, it gives energy to a chemical called a phosphor, which then gives off that energy as light. So you can drive this beam around, and you can draw pictures with it. A rapidly decelerating electron can create some forms of radiation, things like X-rays or very high, quite nasty ultraviolet light. They are reasonably screened, but TVs do give off a certain amount of X-rays, certainly the older ones. So probably sitting right in front of one all the time isn't going to do any good, but not for the dosage isn't very high.
Our next question, Dr. Dave, well, it's about eels. Do you know about eels? Patton Lowestoft. Patton Lowestoft has said, eels are the most marvellous animals. They travel right around the land to get into the ponds that aren't connected to rivers. How do they do it without being seen or without ending up in an eel pie? Oh, poor things. Right, Dr. Dave, what do you reckon?
Yeah, eels have got a remarkable life cycle. They grow up in Europe in rivers and streams. They then, once they get sexually mature after 5 to 20 years, they then swim down the rivers.
They live that long?
Yep. They're quite long-lived. They sit in a river, they grow really big. They then swim down to the sea. They then swim all the way across to a place somewhere in the middle of the Atlantic called the Sargasso Sea. Yeah. Where they breed and reproduce. And they produce lots of little tiny larvae, which slowly then drift back across the Atlantic. And then they swim up to fresh water. They then metamorphose into things which look like normal little eels. And they swim up the rivers as little tiny things called elvers. And then they start living again and live for 5, 10, 20 years. And then they decide at some point that they're grown up enough to go off and breed in the Sargasso Sea.
How interesting.
I mean, I guess there's a couple of ways which they might get into unconnected ponds. One of them is that most ponds which you think aren't next to a river actually do have some outflow stream somewhere,
right,
which they can, even if it's quite a
small
stream or a little, because they're quite small things, the little larval baby elver things, they're tiny little things, so they can swim up through even really small overflow ducts and things.
Oh, right.
They can find a nice place to live in your pond. I guess the other thing which I think I've heard mentioned is they might get picked up by things like herons or other birds, and then somehow get stuck on a bird and then flown somewhere else and dropped off.
They wriggle, I suppose, don't they? Wriggly as an eel. Ooh, interesting stuff. Dr. Dave, Roger Jones has sent an email in, and he says, if you had a rod over 1 light year long, would both ends move together?
So basically, I think what he's asking is that if you've got a really, really long rod, a light year is a distance light will travel in a year, so a hugely long rod. If you push one end of the rod, will the other end immediately move? Simple answer is no. The speed at which information can travel down an actual object is essentially the speed of sound. In the hardest material known, that's diamond, the speed of sound is about 12 kilometres a second. Light travels at 300 million kilometres a second. In fact, it would be impossible for any kind of movement of one end of the rod to be transferred down to the other end faster than the speed of light, basically because the information, the force between the different particles in the different atoms inside the rod is actually transferred at the speed of light. So the absolute maximum, even if you designed the perfect material for transferring force and moving really quickly, would be the speed of light, but it's always going to be a lot slower than that. So, no, nowhere near. It would compress for a long time before the other end started moving.
All right. Let's have another question here. This time this has come in from Mike in Colchester. Gyroscopes, how do they work, Dr. Dave?
That is a very nasty question.
Is it?
Particularly nasty when I can't show you anything. One way of thinking about it is it has a property called angular momentum. And you can sort of think of that as going along the axis at which it's spinning. If it's spinning fast in one direction, then it's got lots of angular momentum along the direction of its axis. Right,
OK. So, like, for instance, if we had a pendant and that was spinning in a circular motion?
So if you had a wheel spinning and it was sitting horizontally.
All right, we've got a wheel sitting in front of us, on its side.
And it's the weird thing about gyroscopes is if they're spinning, if you twist them in one direction, they actually move at 90 degrees to that. So if you twist them forwards, they'll actually twist to the right or left, depending on which way the actual wheel is spinning. So imagine a lump on that wheel.
Yep.
So if you hold something which looks like a wheel in front of you, maybe a plate, and if you imagine that wheel, and if you're trying to tip it away from you, that means that you're trying to lift that lump right next to you upwards. So that gets a bit of speed going upwards. Then the wheel is spinning, so that lump moves around. So maybe it gets to a quarter of the way round. It's still moving upwards. So the right-hand side of the wheel is now moving upwards. It carries on spinning, it's still moving upwards, but now it's opposite you. And now you're trying to, because you're rotating it forwards, then that lump is now trying to be pushed downwards, although it's already moving upwards, so it fights you. So you're now trying to push it in the opposite direction to where it's moving, so it fights you. Now it's moving downwards a bit because you're pushing it forwards and pushing it downwards, and then it carries on going until it's on the left-hand side, at which point it's going downwards. So if you twist it forwards, the right-hand side goes up and the left-hand side goes down, and it doesn't move forwards. If that didn't work very well, then I think I need a diagram. I'm sorry.
That's quite all right. Don't play with gyroscopes. It's simple, isn't it? It's too confusing. All right, let's ask this one here. John in Peterborough says, to add to your last question about TVs, I was messing about with a cathode ray TV that had been turned off for 8 hours, and I still got a really bad electric shock. Be careful, John.
They
Ouch.
use very high voltages, and they have things called capacitors which store charge, and they stay, and they'll store the charge for a long, long time. And they are very dangerous, particularly colour TVs. I heard a story about people who fix TVs, and black and white TVs were relatively low voltage, and they could get away with touching things, and then they transferred over to, and it hurt but it didn't kill them, they transferred over to colour TVs, and they were much higher voltage, much higher currents to make them brighter, and a lot of TV repairmen got killed because they couldn't get away with what they used to be able to.
Because they didn't think of turning it off first.
Or they didn't bother waiting to let it discharge.
Yes. Do be very careful. Don't fiddle with your telly. That's all right.
Tellies are lethal things.
They are indeed. All right. Does the Earth's core use oil as a coolant, like a car engine? Bill has asked this. Can anyone tell me what happens to the hole that is left? We humans drill millions of barrels of oil out of the Earth. Why does the Earth not cave in, as the gap where the oil must be is vast? Absolutely. Bill, well done. So my question is, does the Earth core use oil as a sort of coolant, like your car's engine?
Okay, so what happens when you take oil out of the ground? First thing is, I think you have an image in your head of a great big cavern filled with oil.
Dallas.
So, and then you sort of drill in, and then you suck the oil out of this cavern, and then you've got this huge empty space. It's not quite like that. What it's actually like is you have a big pile of sand or some porous rock, which has got oil in between all the gaps in the sand. This means that when you drill down into this sand, the oil can move through it and up through your hole. And in fact, the thing which tends to push oil out of oil wells is water. So water is denser than oil. Oil floats on water. So most of the ground is sodden with water, because especially under the sea. And so you've got water which is kind of permeating everything. The oil is trying to float upwards. It gets trapped under a cap rock. It's trying to float upwards. You drill a hole in the top of that cap rock, and the water underneath pushes the oil out upwards. And so it squirts out, and the water takes the place of the oil. That's not to say that you don't get some issues with taking lots of oil out, because you've taken some of the volume out. It will be pushing the grains of sand apart a bit. The water which is coming in to take its place is going to dry out higher levels of the rocks higher up, and so you do get a little bit of subsidence in some places. Maybe a few centimetres or up to a metre, I'm guessing, if you took an awful lot of oil out. But yeah, you do get the ground dropping a little bit if you take a lot of oil out. And the Earth's core using oil as a coolant, the oil is very, very near the surface of the Earth. In the top couple of kilometres, most sort of 4 or 5 kilometres, the Earth's core is thousands of kilometres down. Oil doesn't get anywhere near it. The Earth's core is actually cooled by flowing rock, which is a rather different. and the rock does move and sort of convect, a bit like air convects from a convection heater. Hot air rises, hot rock rises, loses heat at the surface, and then goes down. But that's a very, very slow process, which takes millions of years.
How does energy consumption between electric and combustion-powered cars
compare?
Thank you, Danny, for that one.
A normal combustion engine car, I think the efficiencies, basically they convert somewhere round about up to a third of the energy in the fuel into movement energy, useful movement energy. The absolute best anyone's got to, the best internal combustion engines use about half of the energy. The best internal combustion engines we've got are actually the big diesel engines in container ships. Huge diesel engines with cylinders bigger, which you can stand in. And they're actually huge two-stroke diesels, and they are about 50% efficient, but most car engines are at the most 35% efficient, even the really good ones. an actual electric car, the electric motor is incredibly efficient. It's sort of maybe over 90% efficient, 95% efficient. The problem is you've got to create that energy in the first place, and you've got to store it in a battery. You're going to lose a few percent storing it in the battery and then getting it out again. The big thing is how you create the energy. If you're using a coal-powered station to generate the energy, then highest efficiency of that's probably about 50%. If you're using wind power, then it's quite much more efficient. It certainly produces much less carbon dioxide. And I think overall electric cars do come out more efficient than internal combustion ones, but only just. The really big thing is if we can start using renewable energy to power them.
All right, well, a quick email that's come in here from Sean in Beccles. He said, my son has asked me, why do bubbles form a round globe shape?
It's a lovely question. Water, a bubble is basically a very, very thin layer of water which is stabilised by soap molecules. Water has a property called surface tension. This is, if you've ever tried to float a needle on water, this is the fact all the water molecules try and grab together and get as close to other water molecules as possible. And so they try and shrink the surface of the water as much as possible. They pull in. That's the reason why droplets of water are round, because that's the shape with the minimum surface that the water molecules can get into. This little film of water in a bubble is attempting to get into the smallest surface area it can whilst trapping the air inside it. And the shape for a certain volume with the smallest surface area is a sphere. So they form into spheres. If you've got more than one bubble sticking together, then they do all sorts of hideously complicated maths, and they form the minimum surface that you can get with the constraints of the amount of air in each bubble. So you get all sorts of lovely shapes in foams.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.